Hello, my name is Xinyue Zhang, and my topic is Modal Analysis and Canonical Forms. And here is the outline. First, I will introduce modal analysis and canonical forms, then I will give an application of DC motor. Modes are inherent properties of a structure and are determined by the material properties and boundary conditions of the structure. Each mode is defined by a natural frequency, modal damping, and a mode. If either the material properties or the boundary conditions of a structure change, its modes will change. For instance, if mass is added to a structure, it will vibrate differently. Wings of airplanes can be subjected to similar flutter phenomenon during flight. Before an airplane is released, flight flutter tests has to be performed to detect possible onset of flutter. The classical flight flutter testing approach is to expand the flight envelope of an airplane by performing a vibration test at constant flight conditions. Curve fit the data and to estimate the resonance frequencies and damping ratios, and then to plot these frequencies and damping estimates against flight speed or Mach number. The damping values are then extrapolated in order to determine whether it is safe to proceed to the next flight test point. Flutter will occur when one of the damping values tends to become negative. Before starting the flight tests, ground vibration tests, as well as numerical simulations and wind tunnel tests are used to get some priority insight into the problem, which is shown in this figure. Necessary and sufficient conditions for transforming a nonlinear system to a controllable linear system have been proposed, and this theory has been applied to the automatic flight control of aircraft. These transmission results show that the nonlinear properties in a system are often not intrinsic, but are the result of unfortunate choices of coordinates in both state and control variables. If a system is not transformable to a linear one, then the obstruction to the transformation is obvious in the canonical form. If the system can be transformed, it is called a linear equivalent. Then the canonical form is a Euro 1 for a controllable linear system. Therefore, the theory of canonical forms generalizes the earlier transformation to linear system. As is the case in many areas of mathematics, it is often easier to work with the canonical forms than in arbitrary coordinate variables. Now I will give the application DC motor. A DC motor is an electrical machine devised to convert electrical energy into mechanical energy. The applied current converts the electrical energy into the mechanical energy because of the interaction of two magnetic fields. One field is proposed by the permanent magnet, and the other is proposed by the electric current flowing through the armature winding. Because of the interaction of these two fields, the armature experiences a force which tends to rotate the rotor. This is how a DC motor works. For the armature-controlled DC motor position control, the transfer function of the system is derived between the angular position at the output and the applied voltage to the armature of the DC motor as the input. And here are some parameters we will use in this application. The electric equivalent circuit of the armature and the free body diagram of the rotor are shown in the figure. From the figure, we can derive the following governing equations based on Newton's second law and Kirchhoff's voltage law. The differential equations from the above can also be expressed in state space form by choosing the motor position, motor speed, and armature current as the state variables. Again, the armature voltage is treated as the input, and the rotational position is chosen as the output. This figure illustrates the block diagram of the system with the gain matrix feedback loop. In order to calculate the gain matrix K, we can use the controller canonical form. The controllable canonical form arranges the coefficients of the transfer function denominator across one row of the A matrix. The controllable canonical form is useful for the pole placement controller design technique, and here is how we calculate the control matrix K. In this DC motor application, we have the characteristic equation as above. Now, if we set the damping ratio equal to 0.8 and the natural frequency equal to 6, we can get the desired characteristic equation by substituting the given value of the damping ratio and the natural frequency. Therefore, we can get the gain matrix K by the following equation. Here is the MATLAB code. First, I set up the parameters like the first figure, and then I represent the system into a state space representation. And next, I will use the canonical forms to calculate the gain matrix K, and then to have the representation of the closed loop system. Here is the result of the system. The left plot shows that the motor position grows unbounded, in particular that there is no steady state error. The open loop response of the system is not even stable. And the right figure shows that the step response of the system with the desired controller, and the feedback makes the system stable. And here are the references. And that's all for my presentation. Thank you for your listening.